Okay, the first thing I want to bring to your attention about the Chapter 4 test is this sheet is going to be supplied to you during the test, the formula bank. It was also printed out on the practice test. These are all the formulas that are going to have to be used during the test. Not every problem requires a formula, but part of the preparation for this test should be knowing which formula goes with which question. In some cases they're actually named. In other cases you just have to know what you're dealing with to establish what formula you need to use. Those first problem that involves the formulas I think is number 4, but we'll get to that when we get to it. So, number 1 says find the inverse of f of x equals 6x over 2x minus 8. And it also wants the domain and range of f inverse. So what I would do first off is I would establish the domain and range of this function, f of x, and then the domain and range of f inverse, just swap direction of those. So if I look at the domain issue here, we're going to set the denominator equal to 0. And we find out that if x equals 4, the denominator equals 0. We can also see if I put 4 into the numerator, it does not create 0, so it won't be a whole. It's just going to be a value where x is not equal to that. So the domain of f of x is equal to the set of all x values such that x does not equal 4. As far as a range is concerned, you can find the range of this. It doesn't always necessarily match exactly. It really depends on what happens with the graph itself. What I could do to find the range here, what I could do to assume the range is do the horizontal asymptote. The highest power on top is 6x, the highest power on the bottom is 2x. So if I do 6x over 2x, I get y is equal to 3. So that's the value of y that probably won't be taken on. So the range will be the set of all f of x values such that f of x does not equal 3. What you should see on an inverse function of a rational function will be another rational function. Chances are x minus 3 will be on the bottom to create this situation. But again, if I look at, first off, the domain and range of the original function, it helps me to establish the domain and range of my inverse function. Just going to shrink that up a little bit, stick it over here out of the way. To actually create the inverse function, we're going to call this y. And we're just going to swap the x and y coordinates. So every y becomes an x, every x becomes a y. So this y became x, this x became y, this x became y, this 8 stayed 8, this 6 stayed 6, the 2 stayed 2. Next thing I would do is I would want to solve for y. Currently I've got number equals a fraction, so if I put that number over 1 now it looks like fraction equals fraction. Cross multiplication is going to help me simplify this out. So one side is going to be 1 times 6y. The other side is going to be x times 2y minus 8. So it's going to be 2xy minus 8x. Distributive property required x times this and x times that. At this point I want to get y equals. I can either move 2xy to the left or 6y right and 8x left. I'm just going to go 2xy to the left. So 6y stays where it's at, it stays positive. 2xy moves to the left, becomes negative. Negative 8x stays on the right, stays negative. And then if I factor out the common factor of y, I get 6 minus 2x times y equals negative 8x. So y is going to equal negative 8x on top, 6 minus 2x on the bottom. Alright, and that's my inverse function. So I'm going to write it in good inverse function notation. F inverse of x equals negative 8x over 6 minus 2x. The domain is going to equal the set of all x such that x something. And the range is going to be the set of all f negative 1x such that f negative 1x something. Alright, as far as getting the domain and range of this, we're just going to flip these two things. And in order to make the inverse function, I change the y's to x's, x to y, so I swap the variables. I swap the domain and range. The restriction on domain is x does not equal 4. That means f inverse of x does not equal 4. The range is f of x does not equal 3. That means the inverse x does not equal 3. And again, if we check it out, 6 minus 6 makes 0 on the bottom. Obviously, that will be the domain and range. The majority of points are going to come from that. It's an 8-point problem. I'd say probably 6 points comes from this, 1 point each for the domain and range. So if you focus mainly on making sure you know how to find the inverse function, at worst you'll miss 2 points getting the domain and range wrong. Hopefully you get it all right. Number 2, we're going to write log of y cubed over x squared times the cube root of z base c in terms of logs of x, y, and z. And this is just applying our laws of logarithms. The first thing I would do is I would split this apart. I've got y cubed on top, I've got x squared on bottom, and I've got cube root of z on the bottom. So what I would do is I'd do log of y cubed base c. Every top object's positive. I'm going to do minus log of x squared base c. Every bottom thing is subtracted, so x squared's on the bottom, we're subtracting that logarithm. Cube root of z is also being divided, so I'm going to get minus log of the cube root of z base c. So that's the first thing I would do, is I would get it out of the division structure there to create 3 separate logarithms. Something about y, something about x, something about z. Now, this is y cubed x squared and cube root of z. They want x to the first, y to the first, z to the first. So the other step here is we're going to take the powers. This 3 goes in front, this 2 goes in front. And this is actually z to the 1/3 power. Keep in mind that the inside power divided by the root creates a fractional power, so the 1/3 goes out in front. So we end up with a final answer. The logarithm in terms of logs of x, y, and z is going to be 3 log of y base c minus 2 log of x base c minus 1/3 log of z base c. Okay, what I'm looking for in a good final answer, this should be y to the first, x to the first, z to the first, in whichever order. Each of these signs is what they should be, the powers are what they should be, and all the bases are the same as the original base in the problem. Make sure that base c is written for each one of these. And that's what I'm looking for in that problem. Number 3, same idea, going the opposite direction. So here we got everything out of the fraction structure to create a sum and difference. Then we took the powers out. To go backwards, we're going to put the powers back on and stick it back into a subtraction or into a multiplication division structure. So I'm looking at my structure here. Here's my original log of x. Here's my original log of y. And here's my original log of z. So the first thing I would do is I'd put the powers back where they belong. So this is log of x cubed base 2. It says plus, and then I'm going to get log of y to the 4th base 2. Then it says minus, and it says log of z base 2. This one doesn't have a power in front of it, so it just stays log of z base 2. Every positive one belongs on top, every negative one belongs in the bottom. So at this point, I'm going to get log base 2. I have a fraction bar. What belongs on top is x cubed and y to the 4th. Because again, they're both positive. Top stuff is positive. That one's being subtracted. Z belongs in the bottom. And just like that, we have a single logarithm, log of something, base 2. Its coefficient's 1. That's what we're looking for final answer. Those take a little bit of practice, but they're really not that terribly difficult once you practice the technique. Number 4. This is our first time we're going to use a formula, and it says right here very clearly, use the change of base formula. And on that sheet, there's a formula listed as change of base formula. It is log of x base b equals ln x over ln b. If you recall from class, we also have logx over logb. Doesn't matter. I like the ln, so I'm going to go with that one. So they want me to approximate log of 25 base 7. Looking at the formula, the argument of the logarithm is what goes on top, and the base of the logarithm is what goes on bottom. I can identify those two numbers very clearly here. The argument is 25, the base is 7. So this formula tells me that this expression is equivalent to ln 25 on top, ln 7 on the bottom. Then I get my calculator out, and I type in ln 25 in parentheses, divided by ln 7 in parentheses. Be very careful that this is log of 25, only 25, so that in parentheses stops the logarithm from happening. Divided by then ln 7, again the in parentheses stops the logarithm from happening. Hit enter and we get 1.654 174951. Okay, that's the answer. Now it does say round your answer to the nearest 10,000th. When I do specify a specific decimal place I want you to round to, make sure you're rounding to that. And again, this is rounding, not truncating, so we're going to have to consider what's it closest to. If you're not sure about your decimal places, start with tenths, hundredths, thousandths, 10,000ths. This is the 10,000ths place. This is the next number after the 10,000ths place, which is bigger than 5, which means I'm going to round up. Typically on a test, I'm going to deduct a point if you don't round to the correct decimal place. So if you give me the right answer here, you're going to get 7 points. The extra point comes from rounding correctly. Number 5, find the solution of this. For 3 extra points, also find the exact solution. If you only find the exact solution, you get the extra 3 points. You don't have to get the approximate. So if it were me personally and I know how to do this, I would just go ahead and do that. And the way that works is this. We're going to start off with our exponential function. And the 3 and the 5 are the bases. I can't make 3 to some power equal 5 or 5 to some power equal 3. So I can't use the equality of exponents theorem is what it was called. So what I have to do is I have to log both sides. I can do log or ln. Again, I prefer ln. So I'm going to do ln 3 to the 4 minus x power equals ln of 5 to the x power. And what I recommended in class was that we put parentheses around this power because we need to make sure that we remain vigilant about the fact this has to be treated as one object. And then what I do to get this problem to a better level, right now the x's are in the exponent level, is I'm going to throw the exponents out in front of my logarithms because that rule says I'm allowed to do it. So I'm going to get 4 minus x. It's going to be multiplied by the natural log of 3. And that's going to equal x times the natural log of 5. At this point, if you want to get an approximate solution, if you don't want to do the exact solution, you type in ln3, you type in ln5, and they give you decimal approximations. Solve the decimal equation, you're good to go. All right, so what I'm talking about here, if I type in ln3 and I type in ln5, that's approximately what those things equal. So if I take this left-hand side, it's going to be 4 minus x times 1.0986. And that'll equal the right-hand side of x times ln5, which is 1.6094. If I were to solve that equation, I'll get the answer x equals some decimal number. If you're going to go approximate using this, go 4 decimal places in your work, 2 decimal places for the approximate value. If you want to go ahead and go get the exact answer, if we just keep ln of 3 and ln of 5 in the problem as we go, this and this distributive property is going to get me 4 ln 3 minus x ln 3 equals x ln 5. I'd move the x ln 3 over to the right hand side to get the x's together. I would probably go ahead and make this 4 become that power. 3 to the 4th equals 81. You get a nicer number. Anytime you have a number out in front of this, bringing it in as a power to evaluate that, that's probably better. And then over here I got x ln 5 already over there. We're going to move the x ln 3 over to the right. It's negative on this side, becomes positive on that side. ln 81 equals x parentheses ln 5 plus ln 3. Bring it over here. I'm going to get ln 81 over ln 5 plus ln 3 is equal to x. Just divide both sides by the coefficient. And then finally, to beautify it up, to get this exact solution, we're looking for this nice, elegant, correct answer. On the bottom, that makes ln 15. And then that change of base formula in reverse, log of argument 81 base 15 is equal to x. That would be the exact answer in good logarithmic form. If I had gone this route, 4 times 1.0986 comes out to 4.3944 minus 1.0986x equals 1.6094x. Move that over here. That gets me 4.3944 is equal to 1.6094 plus 1.0986. Comes out to 2.708. X, divide 4.3944 by 2.708. We get X is approximately 1.62. That's full credit. This is extra 3 points. So, and if you go for the extra 3 points, that's how I'm expecting your answer to look. Log of some number, base some number, that gets you the 3 points. Don't stop here. Get me all the way to that point. Number 6, solving the logarithmic equation. Now, there's two types of logarithmic equations. One is log, a bunch of log stuff equals a number like we have. The other one is a bunch of log stuff equals a log. Since we have the log equals number structure here, what I want to do is I want to get the left-hand side pushed together into one logarithmic expression by those rules of logarithms. First thing I worry about is powers. So there's no powers. There's 1 log of 3x, 1 log of x minus 1. The other thing I have to consider then is the multiplication or division. We're subtracting the logarithms, so we're going to take the argument of this divided by the argument of that to create 1 log. So log of one expression, which is 3x over x minus 1, base 2, is equal to 2. Now, again, there's two types of logarithmic equations. One is log equals log. If that's the case, argument equals argument. You're ready to go. All right, so if the log equals a log, then this equals whatever. All right, this is the log equals number, so this base raised to that power is equal to that argument. So the argument, which is 3x over x minus 1, is going to equal 2 squared, which is 4. If this was 5, 5 squared is 25. If this was 7, 2 to the 7th equals like 128, I think. But again, this number raised to that power equals this number. All right, so that's not some magical formula that just showed up. It came from this base raised to that power. The fact that it's this way on the study guide, it'll probably be this way on the test. And then finally, if 3x over x minus 1 equals 4, once again we get this proportional structure, so we're going to cross multiply. This side gives me 4x minus 4. This side gets me 3x times 1. Again, x minus 1 is a binomial, 4 times x and 4 times 1. Be careful that we distribute. I'm going to move the 4x over to the right-hand side. That gets me negative 4 equals negative x, so therefore x equals 4. The final step on a logarithmic equation is we verify that this number here, which is our candidate for the right answer, does not create any negative arguments. So the original problem, before I messed with it, is right here. Argument 1 is 3x, argument 2 is x minus 1. If we replace x with 4, 3 times 4 is 12, 4 minus 1 is 3. Both those numbers are positive, so that's a fine answer. If this said x minus 5, obviously we would have gotten a different answer, but if it said x minus 5, 4 minus 5 is negative 1, we'd have to throw it out. All right, so if we do have an answer that doesn't work, put an empty set. In this case, we do have an answer that works, so we're going to leave it as is. Number 7, find the balance on $40,000 invested at an annual interest rate of 6.5% for 7 years, compounded monthly. So let's start off with compounded monthly. Okay, so we have going back to page 1, compounding interest formula, continuously compounding interest formula, going back here to problem number 7, or sorry, yeah, number 7. We have compounded monthly, compounded continuously. So this one uses the top one, the a sub t equals p parentheses 1 plus r over n to the nt. The formula's there. I didn't identify what the variables represent. That's up to you to know that based on your practice and homework and your studies. But a sub t is the balance. So the balance is what we don't know. I'm going to circle this in blue since I'm writing in blue. All right. P is the principal, how much money we invested, and we're investing $40,000. R is the interest rate as a decimal, so 6.5% is 0.065, and again, be very careful with single-digit percent, 6, even though the 0.5, 6%, 0.06, that 5 just gets in there. And then for 7 years, that's what T is. And the other number we need is n, and n is how many times it's going to compound in a year. So if it's compounded monthly, 12 months happen in a year, so n equals 12. So again, it's up to you to know how to find all this information. It will all be in the problem right there in front of you. It's just a matter of finding it. And if I apply the formula as it's written there, what I'm looking for is going to equal what we start with, 40,000 times 1 plus 0.065 divided by 12 to the 12 times 7 power. And this is 12 times 7. Everything's in the power there, so make sure that you establish that before you type it in the calculator. I think 0.065 divided by 12 is going to be some ugly decimal. If I type that in my calculator, it comes out to a non-terminating decimal. I'm going to leave it as that. So I'm just going to type in exactly that in my calculator, what I'm looking at. So 40,000. Pay close attention to what I'm typing and make sure I type it in right. Times parentheses 1 plus 0.065 divided by 12 in parentheses, caret, and then it's 12 times 7. I'm going to put parentheses 12 times 7. If I mentally multiply that to make 84, caret 84 is fine. But if I'm going to put the product in the caret, parentheses, whole product in parentheses, otherwise it just takes the 12th power, multiplies the whole thing times 7, gets you the wrong answer. So be careful that parentheses around both objects there. Enter, and we end up with 62,969.57. We're dealing with money, so we are going to round to the nearest hundredth. So there's part A done. Again, use the right formula. So you have the formula bank there, know how to use it, know what formula to use. For part B, we're compounding continuously. Now we're going to go to the continuously compounding interest formula, which is A sub t is equal to P e to the RT. So once again, A sub t is the balance, which is what we're trying to find. So we don't know that. P is how much money we're investing, still $40,000. R is still the interest rate, which is 6.5% as a decimal. And T is still time, which is 7 years. Everything's the same. The only difference is this has how many times it compounds in a year. Compounding continuously is compounding infinity times in a year. And the formula itself takes that into account. So here's my formula, here's my numbers. So it's just a matter of saying A sub t is equal to what we're investing, e to the RT power. Once again, I've got two things being multiplied in the power there, so parentheses around the whole thing. As far as typing in my calculator is concerned, 40,000 is what we're investing. Make sure we type it in right. To get e to a power, I hit the second button, ln. There's e caret. It automatically puts that parentheses. I want to type both numbers, 0.065 times 7, and then hit in parentheses to make sure the entire power is in that level. We get $63,000, $63,046.94. Recall that compounding continuously always gets you more money than compounding any other way, but not a lot more money. So these numbers should be pretty close to each other, but this number down here, the red number, the continuously number, should be slightly larger than this. We can see it's a little bit less than 100 more. So use the right formulas. Once again, that's the key on that. So number 7, know which formulas to use. Number 8. Find the time required for money invested at an annual rate of 6% to double in value if the investment is compounded monthly. So as soon as you start seeing investments, you want to worry about how it's compounding. This says compounded monthly. Monthly is this formula again. Monthly, daily, yearly, hourly, semi-annually, quarterly, any of those. If it doesn't say the word continuously right here, it's going to be this formula for those problems. Now, when we're trying to double money, if you recall from instruction, I told you to invest $1 and end up with $2. That's the easiest way to double your money. It's not the best investment strategy if you're actually trying to make money, but for the sake of solving a problem like this, invest $1, double it, now you got $2. It works the same if I put $50 billion here and $100 billion there, but the numbers are a lot bigger. So the answer is going to be the same regardless. So when you do a double in value problem, that's how you write doubling in value. What we start with, we double what we start with, that's 2. Once again, we need an interest rate. This is a 6% interest rate, so it's 0.06. And it's being compounded monthly. Once again, there's 12 months in a year, so n is equal to 12. and find the time required. We don't know that, so t is what we don't know, so question mark goes there. So again, every time you do these problems, you pick the right formula. There's my right formula. You identify, there's 5 variables there, identify something for all the variables. You should know everything but one. This is what you're given, this is what you're supposed to assume. Okay, so on a doubling problem, that's what you do. I might put triple in value on the test. If that would be 1, this would be 3 then. So I'm not going to limit myself to saying double, but just know that that type of thing is what you're looking for. So, if I substitute everything I know in, a sub t is 2, p is 1, 1 times anything doesn't matter, that's why 1's useful. 1 plus r over n, 0.06 over 12, to the nt power, that'll be 12t. Okay. If I said semi-annually, n would be 2, 0.06 over 2 to the 2t power. If I said quarterly, n would be 4, 0.06 over 4 to the 4t power. So I'm not guaranteeing that this is going to be 12 on the test. It probably will be compounded in some way that isn't continuously, though, so it'll work like this one does. Next thing I would do, 0.06 over 12 is nice and friendly, isn't it? 0.06 divided by 12 is 0.005. So we get 2 equals 1.005 to the 12t power. Again, that's 0.005 added to 1, which makes that. I will say this, whatever I do, that'll be a nice and pretty division there. So it should work like this does. At this point, I'm at the same place I've been a lot of times when I get these exponential functions. This base doesn't match that base, there's no way to make them match, so I'm just going to log both sides. So ln2 equals ln of 1.005 to the 12t power. 12t, the power comes out here in front. Alright, and what I end up with is ln2 equals, let's go 12 ln 1.005 times t. That times that times that, so that t can be pulled out, and then this is with that. So to get t, I just have to divide this by that. So t is going to equal ln2 on top over 12 ln 1.005 on the bottom. And again, this comes down to entering things in your calculator properly. So show all your work. Give me that right there, you're going to get almost full credit, because that's the right answer. It's just a matter of getting a number value. I'm going to get the number value. That's going to be the last point or two. But when I type this in my calculator, ln2 in parentheses, because that's it on top, divided by, now 12 times ln 1.05, that's two things being multiplied. I have to put a parentheses for the bottom, 12 times ln 1.005, in parentheses for the log, in parentheses for the denominator, equals. We get 11.58 years. So around the nearest hundredth of a year. So again, if I look at the number 11.581311013, alright, that's my number. Nearest hundredth of a year, there's my hundredths place, there's the next number 1, so I would go with 11.58 years for that one. Alright, but again, show your work, write down the formula you chose to use, write down all the pertinent information here, write down where you've substituted all the pertinent information in, write down where you solve the equation, get a nice pretty answer like that, and then give me this decimal. This right here is worth probably 6 out of the 8 points. That's worth the extra point, and rounding it right is worth the last point. Number 9, what to the nearest tenth will an earthquake measure on the Richter scale if it has an intensity of 7,943,121,396 I sub 0? We're looking for earthquake magnitude. There's a formula on the sheet that says earthquake magnitude. It says that right there. And it does say round to the nearest tenth. So again, not rounding correctly is going to cost you a point. Anytime you do earthquakes, it's always like 2.7 or 5.9 or 9.2. They don't go 9.23. So make sure that you do round to the nearest tenth. So for part A, the magnitude is going to equal the log of 7,943,121,396 I sub 0 over I sub 0. Remember, log with no base, that's understood to be base 10. I'm going to put a base 10 there, it doesn't hurt. They always give you intensity with a little I sub 0 on it. That divides by the I sub 0 in there. So basically you just have to log that number to get the magnitude of the earthquake. So log this time, because it's base 10, 7, 9, 4, 3, 1, 2, 1, 3, 9, 6. Again, do some checking for detail here. Make sure that this number matches that number. And we end up with 9.9. So 9.89999912. But again, that to the nearest tenth is 9.9. Question B here says compare the intensity of the earthquake in part A to the intensity of earthquake measured 6.2 on the Richter scale by finding the ratio of the larger to the smaller intensity, round to the nearest whole number. So what we're doing here is an intensity comparison. And if we start by looking at the magnitudes, 6.2 and 9.9 for part B, the difference in magnitudes is equal to 3.7. Subtract 9.9 minus 6.2 equals 3.7. And then again, using the same formula, I'm going to write 3.7 is equal to log of I over I sub 0. And again, that's base 10. Which means if I change this logarithmic to exponential form, 10 to that power is equal to that. So I over I sub 0 is equal to 10 to the 3.7 power. So then I just type that in my calculator, 10 caret 3.7. This says round to the nearest whole number. So I see it's 5,011.872336. Nearest whole number is going to be 5,012. So this says I over I0, but it's really I intensity of top earthquake over I intensity of bottom earthquake. Comes out to 5,012. So that tells me that the 9.9 earthquake is exactly this much, or approximately this much bigger intensity than that. So as far as finding the ratio, we're going to say that 9.9 is 5,012 times more intense than 6.2. That's how I'm expecting to see your answer on the test for that. All right. If you get the wrong answer in part A, but you get the correct ratio of the two magnitudes in part B, you'll get full credit for part B, even though you have the wrong answer for what I gave you. But I don't expect anybody to get the wrong answer in A unless they type something wrong in the calculator. So do part B based on your answer from part A. And again, if you have the wrong answer from part A, you'll lose some points for that, but you'll get full credit for getting the right thing there. Number 10, find the exponential growth function for a city whose population was 23,200 in 1992, 61,200 in 2001. Use t equals 0 to represent 1992, round k to the nearest 10,000. So find the exponential growth function. That's what it says. And there's a nice little formula on our first page that says exponential growth or decay formula. So we're going to use that formula. Again, most of these formulas are pretty straightforward. Our exponential growth or decay formula. Now, we again have to know what these variables mean. So n of t is the final amount. N sub 0 is the initial amount. E is the letter E that we always use. K is the constant of variation, and t is the amount of time in years. All right, so what we're given in this problem is that we have some city that we start off with an initial population of 23,200. We end up with 61,200 in 2001, which is 9 years later. They want 1992 to be represented as time equals 0. All right? So looking at all the stuff I need to establish here for part A, my final amount is 61,200. My initial amount is 23,200. I can see that from 1992 to 2001 is a total of 9 years. And finally, k is what we don't know. But it does say round k to the nearest 10,000. What they want is this formula here. They want this to remain a variable and this t to remain a variable. They want k and n sub 0 to be K and N sub 0, whatever they are. So obviously N sub 0 is 23,200, K is what I don't know. So what I'm going to do is I'm going to substitute that stuff into this formula to figure out what K should be. So 61,200 equals 23,200 e to the K, which we don't know yet, times 9. And then if I divide both sides by 23,200, I get to here. I like to get fractions in these problems to get a nice, pretty exact decimal at the end, or really close to exact decimal that I can round. So I'm going to type in this, 61,200 divided by 23,200. And if I hit the math button, the very first thing in the list is frac. That just changes it to a reduced fraction. So 153 over 58 is equal to e to the 9k power. At this point, I've got e to a power equals. I'm trying to find out what the power is, so I'm going to log both sides. And again, I'm partial to ln anyway, but if I have e to a power, I always use ln because, let me just walk you through this. ln of e to the 9k, that's log base e of e to the 9k. These are the same, so the answer is 9k. So if you ln e to a power, you just get the power out. It's just so much easier to deal with. And then finally, we're trying to find out what k is. So if I just divide by 9, there's k. That's exactly what k is. If I want to get the approximate value to the nearest 10,000th is what it asked for, if I remember right. Let me just glance up real quick. To the nearest 10,000. So we want a decimal approximation here. ln 153 divided by 58 in parentheses. So again, I'm logging that entire fraction, then dividing that log by 9. We get 0.1077772123. If I'm rounding to the nearest 10,000, that's 0.1078. All right, that's what k is. So what they want me to do with k, again, if I look at the question, they want me to write the exponential growth function for this city. And what I'm looking to do is I'm looking to replace in the formula here, let me just erase that. If I'm trying to write an exponential growth function, I want n sub t and t to be variables. I want n sub 0 and k to be numbers. So I can see very clearly n sub 0 is equal to 23,200, k is 0.1078, so I just write that function out like so. The final amount, n sub t, is equal to the initial amount, 23,200, times e to the k, 0.1078 times t. Okay. What that does for me now is if I know how many years has passed, I can predict what the population would be. If I know what the population is, I can predict how many years it's been. So that's what the purpose of that is for, and that's again the answer to part A. That's what it should look like. For part B, it says to use the growth function, this, to predict the population in 2009. All right. Now, considering that t equals 0 is 1992, we have to ask ourselves how many years passes from 1992 to 2009, the answer being 17 years. So I simply have to do n of 17. So that's going to be 23,200 e to the 0.1078 times 17. And that's just something I can type in my calculator. Just like that. So if I come over here and type in 23200 times second ln, so that's e to the power, and then 0.1078 times 17 in parentheses. Both the 1078 and the 17 are in the power because that's where they are. Make sure that they end up in the power. Hit enter. It comes out to 145,002.6878. So you can get your number on your calculator. Then it says round to the nearest 1,000. There's the 1,000 place. The next number is 0. So we're going to go 145,000 people. We're going to predict that many people in 2009 in that city based on the population growth from the previous years. Number 11. Determine in the nearest 10 years the age of a bone if it now contains 71% of its original amount of carbon-14. The half-life of carbon-14 is 5,730 years. So we have the half-life formula on our sheet. It's right there. P of t is the percentage as a decimal, and t is the number of years that have passed. So if it contains 71%, that's p of t, so we're going to go 0.71 equals 0.5 e to the t over 5730. So to get the half-life here, or I should say to get the amount of time it took to happen, we're going to divide by 0.5 on both sides. 0.71 divided by 0.5 comes out to 1.42 equals e to the t over 5730. Once again, e to a power equals a number, so I'm going to log both sides, ln. ln of 1.42 is going to equal just the power, t over 5730. And then I just have to cross multiply. 1 times t is t, and 5,730 times the natural log of 1.42 is my answer. And then of course I have to actually get a decimal approximation for that, so I get my calculator back out. 5730 times ln 1.42 in parentheses equals, comes out to 2009.263874. That's how many years it would take to be 71%. They said to the nearest 10 years. There's my tens place. So that's going to round up to 2010. So t equals 2010 years. All right. I will give you the same kind of problem. I'm going to change the percentage. So it might be 72% or might be 43%, whatever. But the percent as a decimal equals that formula, and then just solve for t. Number 12, the population of banana slugs in a state park satisfies a logistic growth model. So going back again to page 1, which again is supplied for you. Logistic growth formulas. So it says logistic growth model, so it should bring to your attention, hey, we got some formulas here. So we're going to look at those two formulas. P of t is equal to c over 1 plus a e to the negative bt, where a is equal to c minus p sub 0 over p sub 0. P sub 0 is initial population, P of t is final population, c is carrying capacity, a is this number, and b is another constant that we have to find usually. So, if we take a look at this problem, I'm going to shrink it up so I have room to work. Population satisfies logistic growth model, P sub 0 is 275, P of 1 is 350. P of 1 just means after 1 year, so that means t is equal to 1 year. Carrying capacity is 2,200 banana slugs. And we want to find the logistic growth model. So again, logistic growth model, they want you to create this function. They just want to know what a, b, and c equal. All right? C we know, they gave it to me. A I can find because I know c and p sub 0. B I have to find using all this stuff in the process. So if I were to figure out that A is equal to the carrying capacity 2,200 minus A, which minus P sub 0, which is 275 over 275, that comes out to 2,200 minus 275 equals, divided by 275 equals 7. That came out to a nice pretty number. If it comes out as a fraction, leave it as a fraction. And again, let's say it was like 15 divided by 27. Let's say something weird like that. Math, frac, enter. And then it gives you 5/9. I'd rather have a fraction than a decimal there for A. So A is 7. And again, here's my formula. The final amount, 350, equals the initial amount, equals the carrying capacity, 2,200, over 1 plus A, which is 7, e to the negative b, I don't know yet, times t, which is 1. So C is 2,200, A is 7, T is 1, final amount 350. It gives us this nice little equation here. If I put this over 1 and cross multiply, one side is going to be 2,200, that's the easy side. The harder side, 350 times 1 is 350. 350 times 7 is 2,450. E to the negative b. Alright, so to finish solving this out, I want to get e to a power equal, so move the 350 over here. So 2,200 minus 350. Get 1850 is equal to 2,450 e to the negative b. Divide both sides by 2,450. If I do 1850 divided by 2450, math, frac, enter, 37/49. So 37/49 equals e to the negative b. So if I log both sides, ln of 37/49 equals negative b. Change the signs. And if I do negative ln of 37/49, we get b to be 0.28, or sorry, k, yeah, b. Yeah, b is 0.2809. Round b to the nearest 10,000th, so 0.2809. So b is that, a is that, c is that, and again, I want to create this formula here using those numbers. So I can get my final population, P of t, equals carrying capacity over 1 plus A7 e to the negative b times t. So that's part A. We're looking for a logistic growth function. There it is. Part B, predict the population in 2015. Now, the initial year is 2001, so 2015 is 14 years later, so P of 14 comes out to 2200 over 1 plus 7e to the negative 0.2809 times 14. So then again, it's just using our calculator, but being careful about typing it in correctly. So if I type in 2200 divided by parentheses for the denominator, so this whole thing is in parentheses here, 1 plus 7 times e caret. Now, oops, automatically puts the parentheses there for me. E caret parentheses. The whole power is negative 0.2809 times 14. End parentheses for the e to the power, end parentheses for the denominator. We find out the population should be right about, said, predict that. We're going to round to the nearest whole number, so 1,935 banana slugs. Finally, the bonus. I'm going to make the bonus related to the logistic growth model we just did. And what I'm going to do is I'm going to ask you what year it first reaches 2100 in this case. Obviously it's after year 14 because it reached 1934, then it's growing. It'll eventually reach 2200, but I want 2100 rounded to 2100. So what I want to do is find out what year that happens in. So if I just take this y equals and type in my logistic growth model. So go back here and type that in. So 2200 divided by parentheses 1 plus 7 times e to the negative 0.2809 using x for t, end parentheses for the power, end parentheses for the denominator. Come over here to my table and just start throwing numbers in. Just to guess and check really for this bonus. All right. So we know it's after 14, so 15 is 1993. Let's go 20, 2145. It's between 15 and 20. 16 is 2040. 17 is 2077. 18 is 2106. So it happened within year 17. So 18, it's already over. So between 17 and 18, so somewhere within the year, 17 years later. So we know t is equal to 17 years. And we started in 2001, so that gets us 2018 will be the first year the population reached 2,100. Again, somewhere within the year 2018. By the time it's 2019, it's over 2,100. So that will be the answer I'm looking for there. So, and you can't show work on that, but give me the right year and you'll be fine. If you give me an improper answer here, but use that properly to get this answer over here, I'll probably give you full credit for the bonus. So at least have a logistic growth model, at least have some answer here that I can use to establish your correct or incorrect answer on the bonus.